Um, Hello. In this video, we're going to be continuing with the Tesla cavity and conducting a multi-pattern analysis on the Tesla cavity. Now you have this paper here, which I would also leave in the description, the link to this paper in the description. So in this paper, basically, they studied high field multi-pattern of the Tesla, the 1.3 gigahertz Tesla cavity, and they use the multi-pack code, which is a 2D code, and they were able to predict multipacting. So I would show how this can be done using the CST particle in cell solver to conduct the same analysis. So first of all, just a brief definition of multipacting. So in this paper, I really like this definition. The multipactor effect is a phenomenon in radio frequency devices where under certain conditions, secondary emission electron emission in resonance with an alternating electric field leads to exponential electron multiplication. So basically, this just means that for a cavity or any other RF device, you could have some kind of conditions met such that when maybe an electron or multiple electrons are emitted from any part of the surface, these are driven, of course, because they're charged particles, they're driven by the electric field, and then they hit on another part of the wall of the cavity. And then under certain conditions, if the secondary emission yield of the material is such that it allows for secondary emissions and at the right electron energy, then you have that secondary emissions are emitted. So let's say an electron hits the wall, and then maybe secondary emission condition is such that two electrons are released. So you have such a condition, and that's basically multipacting. So we'll see how we'll do that with the PIC solver. Now, since it needs the simulation would need a high mesh refinement, I am just going to analyze for the mid cell of the cavity instead of conducting eigenmode analysis for the entire cell, as it would save more time. Now, second thing to note, or the first and most important thing, is that multipacting analysis using PIC solver, you would need a hexahedral mesh, because you would first of all calculate the field you could do this in time domain, or you could use the eigenmode solver. I'm going to use the eigenmode solver, and then you have to export the fields to the particle in cell solver, which is a time domain solver, and that supports only hexahedral mesh. You could do it with tetrahedral mesh, but it's not very ideal. Or you could try, I tried once, but then the results, I think there was a problem with the results, and I just concluded without further looking at it that it must have been because I used tetrahedral mesh, because in the end the results would have to be interpolated onto the PIC solver. So we'll be doing two separate would be opening two separate files. So this would be for the eigenmode analysis, which I'll just call Tesla mid-cell, or maybe I should save this and create a new one, and I'll call it Tesla mid-cell hex. I'll call it hex. So eigenmode, I'll just put eigenmode, and then a second one which I would call PIC particle in cell. So instead of working with my mid-cell geometry, okay. So now we have this, and yeah, we could go right ahead and perform our eigenmode simulation, which is not really a big deal. So you already have your model. You just have to make sure your boundary conditions. So I'm going from, I just need one mode, so really small, 1290 to 1000 frequency range 301, and then my background pack. Okay, confirmed. I think I already said this, but just to confirm, then magnetic symmetry planes. Now I'm going to apply symmetry planes just so I get more refinement, and then lastly, let's see, I'm going to change my mesh. Yes, to hexahedral mesh, and I'll just click update because okay, now this multipacting simulation is mesh sensitive, and I'll show you why. if you should have a look at this paper, you see that multipacting it's a local event, at least for cavities. It's a local event which occurs just at the equator. So you see it's about 0.2 meters. No, that doesn't look right. This cannot be meters, and this would be 200 millimeters. No, this doesn't look right. The axis, for the axis to be in meters. Okay, times 10 raised to power minus 3. Okay, so this is 0.2 millimeters. Yes, so times 10 raised to power minus 3. So 0.2 millimeters. So it's pretty much a local event. And then if you do not have your mesh refined, you wouldn't really observe multipacting at that point, because of course your field will be interpolated wrong, and then you have all sorts of problems. So because of that, it's very important to have highly refined mesh around the equator region, because we already know where multipacting is likely to occur. To do that, I would instead of refining the entire mesh, I would do a local refinement, and for that I would okay, I think I'll just combine this with a plus. So instead of going to boolean and add, you could just press a plus on your keyboard, and then this adds it. That's if you have the numeric keypad. So I am going to copy this. Now one very important thing, if you want to copy a model in CST, it is better to, because you could Control C and then Control V, paste it. But then I've run into problems with this when I try to edit my history. It doesn't really work so well. So instead, just go to translate and copy, and then just translate to 000, so it creates another one, and I click OK. So you now have a different copy, and this is so none to all. And this is better than copy and pasting. So I have a different solid in there, and now what I want to do is I want to remove some region from it. So because I just want to apply mesh refinement to a particular, just the equator side, so I would go with okay, I need alter radius REQ, Z mean I'll just put 2 times L minus 2 times L, because I want to cut off, you'll see once I'm done 2 times L. So if I should preview, yes, then X center now 0. So I want to cut off most of the parts of the cavity and just leave the and leave only the, oh, I think I should orient it in I just want to leave the top part, but then this wouldn't work, because if I reduce my radius, it would reduce the other thing. So what would I do? I would use a box instead, or use a brick. So I go X mean, let's say REQ, and REQ. I just put minus. It should be minus and plus. So on both sides. So then this will be 2 times L minus, and then plus 2 times L. So if I should preview that, then I have this, but then I'd have to adjust to Y. So let me say 10. Now that's a bit too much. Let's say 7.5. The reason why I'm so careful is because this is if the region is too much, then you have a large number of mesh that takes a lot of time to compute. So I think 7.5 should be enough, should be okay to capture that region. And then I click on okay, yes, none to all. And then what I'm going to do is subtract this break from solid 1. So I just click on solid 1. I could either go to boolean subtract, but then I could also press, you'll see here the shortcut minus. So I click on minus, then I click on solid 2, which is the break, and then so what I have is this, just this part, and I'm going to be applying mesh refinement to this. I mean, you could in principle still cut off this side, because the multipacting is just on a plane. It mostly occurs on a plane. but then I'm just going to leave that. So I would apply local mesh refinement to this, right click and go to local mesh properties, and I want the absolute value to be 1 millimeter, the step width to be 1 millimeter, and let's see what this looks like. Go ahead and update the mesh, and not too bad, but then still not fine enough. So I'll go ahead and change this to, or I could just go to mesh view and local properties of this and change it from 1 millimeter to 0.1. Let's see. Okay, I think this is going to be a lot. Yes, this is 18.54 million cells. And then what I'm also careful is you have the staircase approximation of the geometry, which is not very good if you have a mesh that is not so fine. So 18 million cells, so you could see it here. Oh boy. Oh, my video went off there. I don't know why, but yeah, I hope it's back now. So 18 million cells. I don't want to run this forever. I'll keep it at, let's say, 0.22 million. Okay, I think that's okay. But then when if you're doing a real analysis and you use it at, yeah, whatever you want, I think this is enough. I hope I am correct. 2 million cells, that's manageable. 2.9, almost 3 million cells, that's manageable. So I think I might increase also the mesh resolution here, so maybe 20, so that would also increase. Let's see, 30. Okay, 4.7. It's still a bit much, but let me see how long this would take. I would start the simulation now. So that's it for the eigen mode analysis. So I'm going to let this run while I prepare the other model for the particle in cell simulation, the PIC simulation. So I think I have everything set, and yes, I can just do JDM. And one mode and 1 to 90, consider post-processing. Yes, I'm not doing any refining. I'll just go frequencies above. Yes, I hope I did not make any error and start this. So yeah, it solves for the field. So while that is running, I'll go over to the second geometry, so the PIC. Now for the PIC simulation we need an actual material, so we need to define a material surface. So I'm going to go ahead and shell this so I can apply material to it. So I'll go on F, and then so I click on F on the keyboard to select face. Maybe I should put show key press here somewhere for those I've forgotten. So F, or you could go to modeling and peaks and then face. So you see all the shortcuts, F, Shift, F. So done with that, and I'll go to, well, first of all I need to, so I press on D to deselect everything. So first of all I would have to add the components, and then F, and let's see, what I need to do, shape tools, and then go to shell or thickening, and I could use any thickness here. Let's say 2 millimeters. Preview and outside, and yeah, that's it. So we have cavity geometry, but the material is still vacuum. So go ahead and change the material to, so right click and assign material, component, and color. Now I'll go to load material from library. Now I already defined niobium, but I don't think it comes with CST. Now I'm thinking of how I would give you the properties of this, and I can't upload files to YouTube. I think I'll just show the material definition and then you could pause. Yeah, So this is okay. So that's niobium. Now, but I can't think of a way to currently to share the file with you that you could copy to your CST materials folder, but I would show you the material definition. So for the general, you have this definition, but I mean we don't really need this. Then for the thermal, this definition also, we do not need this or this analysis. Mechanics, we don't need this, but then these are the properties. And then no, am I clicking the correct material? Yes. Density, no, something is not correct. There should be particles. There should be particles here. So this I'll just go back to materials. Something is not right here. I'll pause and then check what the problem is, because there should be particles, because you see here you have the secondary emission yield, which is all of this, but don't seem to have that defined here. I'll just go ahead and pause and check what's wrong with that. Okay, figure out what the problem is. The problem is in this particular simulation we do not need particles, so I still haven't changed the simulation type from eigen mode solver to particle in cell. That's why some material options are not available. So I go to problem type, particle in cell, PIC, and I change it. Then I have the PIC solver. Now if I should go over to the materials, yes, now I have particles, the particles tab. So every other thing remains the same, but then you have this particles tab. So um, I think the property was none initially. I mean, by default, if you should create the material, it should be none, but then you want to change this to secondary emission and then change this to the. Oh, now my webcam is off again. I don't know. I think there's an error with my camera. Okay. Yeah, as I was saying, foreman, or I mean, if you're more advanced, you could also. Oh boy, it's gone again. I hope it doesn't go off again. It's reporting an error, but yeah. So the secondary emission model, foreman model, or if you're familiar with the Vaughan model, I will stop again. Sorry about that. I don't know what's wrong, but hopefully it doesn't. I just hope it doesn't go off again. So foreman model, then you go to the true, and then these are the settings. I don't know if you would need more of these. I think it would be, yeah, so this you could just pause and copy all of this, and then you go to the elastic, then you get these, and then diffuse secondary emissions, you have these settings, or you could import your own. If you have an SEY curve, you could import it here. But yeah, and then these other settings, you have them like this. So yes, so now I can't remember where I got these. I can't remember where I got these from. I think maybe you could just look up foreman, maybe foreman model niobium. I don't know, I'm just foreman SEY model, because I saved that a while ago. Yeah, so I think, yeah, it's something like this, but yeah, maybe you could get the settings from this paper or something. I don't know. Now it's off again. Okay, I couldn't get the camera to work. This is my first time using this camera, so please bear with me. I think I could just continue. So yeah, the eigen mode analysis is still running. I hope this is still recording. I hope. So yeah, so that was the material properties, the most important one being this, and then you could see the SEY, secondary emission yield curve, which it draws from those parameters. So yeah, and where were we? Yeah, so we've set up the material, and now we need a particle source. Now for the simulation, so frequency, I think, okay, yeah, the same. Now for the background, you'll have to change the background because you already have a background, a wall material, so you change the background to normal. And yes, so make sure to change it to normal, and then otherwise you get an error. So this doesn't work with symmetry planes. So if you had symmetry planes, remove it, otherwise you run into errors. And okay, and yes, that should be that, but then we need a particle source, and I'm going to click on this. Now I'm going to put a particle source at the equator because I know that yeah, that's where the multipacting would occur. So I'm going to cut this and place it at the equator. Now you could, okay, I'll get to that. I'll just change it to 100. You could change it to 1000. I don't really know what it controls. I guess the emission area, like this. I mean, when you preview it, you see it. So if you put a 1, it's a very small area that you emit from. So leave it at 100. You could also put it at 1000. And then you see the direction of emission, and which is to the z-axis. So you want to change that, and you change that by putting it to normal to -y, so it emits downwards. So that's that. And then you want to set your you want to go into your emission settings and do not touch. Okay, I think I could change this to maybe -17, the total charge on the bunch, and leave it at one bunch, and yeah, I think that's sufficient. And then this I change it to 5, so that's the initial kinetic energy of the particles. Now the kinetic energy spread, I want it to be 100%, so 100% from 5 electron volts. That would be I don't know. Can calculate 100% from 5 would be how many? So plus or minus 100%, so 10 and 0. Yeah, or I could leave it at 50%. 50% would be 2.5 and 7.5. Yeah, I think I'll leave it at 50%. And then angle spread, so emission angle 45. So that defines the angle from your reference angle, which is the -1. So it has a 45 degrees angle spread from this axis. So it would be something like total 90 degrees. I hope that's correct. I hope it's plus or minus, not just one of them or the total. Because if you do the total, it would be 90 degrees. Okay. So that's that. So we have the particles electron. You could also change it to protons if you're working with protons. So I think that's all for the setup. So that's all for the PIC setup. The last thing you need to do is, of course, to import the fields, which would be your driver, your particle driver. So you go to source fields and then import external field. Now our eigenmode simulation is still running, so we do not have fields yet. So while waiting for that, I think I'll have to pause at some point, but while waiting for that, I could show you the other particle sources. So you could have an area source where you could select an area, a particular area, surface area, and then electrons or particles are emitted from the entire area, and then you have different definitions. It takes a while to okay, I'll just click on it. So if I wanted to emit from this area, it takes a while to triangulate the surface depending on how large your surface is. You could have this, so instead of having just one point source, you have multiple distributed over the area. This takes a bit of time. So for this case, since I know that the multipacting occurs at the equator as it does for all elliptical cavities, that's why I just defined a point source. But then maybe if you were not sure, you have a new device and you're not sure where it multipacks, then you could use the area, just to have a large area. So you have number of emission points. Instead of one, you have 3580. Then if you should go to edit, you have the same properties as the same menu as you had for the single point. So that's defining the Gaussian emission, and then you could also change it from this to DC field or explosive. I don't know what those means for now. And yeah, I changed this, and that's that. Then you could also have circular source. So for that you have a kind of, let's see, if you had, yeah, a circular curve, then you could in principle emit from the entire equator region. Oh no, not equator region. So you have a circular source, just this, which is like a face, and then it distributes the emission points around the face. So this could be good for maybe the inlet of a device or something. And yes, then you also have particle source by volume. I think this selects a volume, and then particle import interface. I don't know what this does. I've never used it, but let me see what it. Okay, I'm not going to get into all of that. Just trying to wait for the simulations to run. 1 out of 2. Okay, I'll go ahead and pause here, and once the eigenmode analysis simulation is done, I'll be back so we can import it into this. So just deselect this and Shift C to. So use your Shift C to get a section view or toggle out of a section view. So see you soon. Oh, not see you. I'll be back soon. I'm just going to pause now. Oh, and before I go, I'll just set the mesh properties now. The mesh at the mesh for, you don't only need to have fine mesh for the eigenmode simulation, but also for the PIC solver. Now I think I made a mistake. I should have before shelling, I should have refined also at the equator. But then let's look at the mesh. Okay, that's not fine enough. And if you should have this, then you would have pretty wrong answers. I mean, some places you might not expect multipacting, you might see, or you might not even notice you might not, the software would not give multipacting when you know that it actually multipacts this. So to rectify this, I'll pause this and go ahead and go back in the history, or should I show that? Maybe I'll go back in the history and let's see, shell object before I shell the object. So this is how I make a modification. So before I shell the object, I'm just going to make a copy, and that's translate, remember, and copy, and okay. So non-zero, and I go back and I just continue. Yes, close. So I went back in time and yeah, I have this second solid which I can now cut and then apply what's it called, apply a local mesh refinement. So I'll go and create a brick, and the same as the last time, REQ, and this is 2 times L, and this is minus 2 times L. Let's preview this, and then I want to reduce this by, well, how much did I use? 7.5. Yes. I mean, the way I could have done this is just wait for or import the hex model, but I totally forgot. So I'll just go here and then click on solid 1 negative and click on this, and yes, now I have this too. Now you don't need to bother about what it does here because it's basically normal. The material is assigned material colors, it's vacuum, so it doesn't serve any other purpose aside for mesh refinement. So I'll go ahead and apply local mesh refinement, and I think we use 0.2 for the other one. Okay, 0.2, and yeah, that should be that. Now let's view the mesh global properties, and then I think this was set to, was it 50? Wait. Oh, 15 million, that's a lot. um 15 million, just so that I don't run this forever. I mean, I hope even with a bit coarser mesh I could have the multiplexing result, otherwise I'll just show an old result. I don't want to run this for a very long time. So 6.9 million, a bit manageable. Let me make that 0.35. So this defines the maximum step I think I already mentioned. So a millimeter, so 0.35 millimeters, 5 million. Let's see how coarse this is. I think this is okay. It's manageable. If you just a note, if you run the multiplexing simulation and then you are sure that multiplexing should occur at a particular fit value and it doesn't occur, then you should look at your mesh. You should make sure you refine your mesh very well, just to eliminate that. So just to eliminate that from the list of possible causes. I think it's not very fine, but let's see. I think it would. I hope it works. So yeah, the eigenmode analysis is still running. One problem with a very fine mesh. So I'll just pause, and I think we're done here. And we'll just have to. And this is another problem with this is one problem with hexahedral mesh, is that you can't really have a local refinement without it extending all the way to the end. So yeah, we'll just have to manage that. So yeah, I'll pause this and yeah, come back when it's done. So the eigenmode simulation is done, and then from the log file, so we should go to home tab and look at the log file. You'd see at the runtime was 6 hours. So it took 6 hours, almost 7 hours, 6 hours 51 minutes to run this. So like I said, really computational intensive. So now since we're already done setting up the particle in cell solver, we would just have to, what was left was importing the fields. I mean, I don't know if you noticed, but this is another day. I couldn't wait for the simulation to finish running. So I'll just go and import external field. I think we applied let's see, symmetry boundary conditions. Yes, we did. So in importing the field, you'd have to take that also into account. So I'm going to add this from project, and if I should add from project, then I'll show how to add from project and the other one. Let's see, YouTube videos. I think this should be where it is. And then no, where is it? Okay, that's in Tesla. So hex again and then open. So it's, you have the modes, which is just one mode which you calculated for, and that's I import the E. Now if you were to be importing from, so this already takes into account your symmetry conditions and does everything nice for you, but if you were to import from a file now I don't know if I can see the file. I think results, yes, so you have your E file and your H file. So if I were importing from a file, then okay, okay. If I were importing from a text file, then I would have to specify the symmetry planes, as if you exported your fields from your eigenmode simulation to a text file. Then you would have to specify the symmetry planes, but then once it's your M3D file, which is the default that your CST writes for only hexahedral meshes, then it comes with all the information that it needs to mirror the fields or any of those things. So I'm just going to go ahead and add from project again. So I need the E and the H fields. So going and then I get H field, and that's it. So it gets the frequency, then the factor, and everything. So that's that from adding the source field. Now your eigenmode simulation is normalized to 1 joule of energy. So you have this range of electric fields, and then from here you could find your E acceleration. I think I did this in the other video. Oh, I don't have the results here, so I'll just go ahead and quickly do a post-processing for that. So for the E acceleration, I want to go to eigenmode result. I've done this in a previous video, that's why I'm rushing through it. When I go to voltage for mode 1, Z, consider particle velocity and evaluate that. So I'm evaluating the on-axis voltage, and then I would go to mix. So 1D result, and then mix template results, and then divide it by the length. So this would be voltage divided by length. So converting to, so this should be V divided by length. Length is 2 times L times 1e to minus 3 to convert to meters. I hope that's correct. So this should be your E acceleration. Yes, so that's 8.314. What I do sometimes is, because just looking at this result on its own, one can never be too sure, but I'm just going to trust that it's correct. What I do sometimes, or most times, is to also evaluate the peak field, and then calculate the peak field to accelerating field ratio, because that is independent on the scaling of the fields. So but for this, I'm just going to trust that it is correct. So what I have is 8.34 e to power 6. So the field I just imported, the accelerating field is at 8.34 e to power 6 volts per meter. So that's 8.3 megavolts per meter. But if I go back to this paper now, if I can find it again, multipacting was predicted for the field range of, so this is the peak field, so times 10 raised to the power 4. So if you divide by 2, then you have the value in terms of accelerating field. So this would be about divided by 2, that should 5, that 2. So this should be 20. Is it? Am I correct? So this is 40 divided by, okay, it's not, it's because this is times 10 raised to the power 4 kilovolts per meter. So converting to megavolts per meter, this becomes 40 megavolts per meter. Yeah, divided by 2, that should be 20. Yeah, around 20 megavolts per. So this is 25. That seems wrong. Okay, because the operating field for the Tesla cavity should be 25 megavolts per meter. So having it close, which would be divided by 2 here, that there's a chance of multipacting of that. Okay. Oh, I think this is a different one. No, but it's a 1.3 gigahertz cavity. Okay, I'm just going to go with this, and so the accelerating field would be the peak field ratio of the Tesla cavity is 2.0. So to convert this from peak field to accelerating field, I just divide by 2. So this should be between 20 and, or this should be between 15 megavolts per meter and 30 megavolts per meter. So the maximum occurs at around, let's say, 48. So that would be 24 megavolts per meter. I just hope I'm correct. Now we am 24, 48 divided by 2, yeah, 24 megavolts per meter. So I have to scale this imported field. So this field that not excitation signals, the fields I imported just now, I have to scale it before running the simulation. So it's currently at 8. So I'll go to calculator, where's that calculator? So it's currently at 8.3, so I want to evaluate it at 20. Let's see, none of this. How did I say just now? 24 megavolts per meter, and check for multipacting. So this would be 24 divided by 8.3. And one thing you should take note of is the units, because this is 8.3 e to power 6. Sometimes it might be e to power 5. That's from the eigenmode analysis, so just take care. And so calculate. So the factor should be this. So I'm just going to go ahead and copy this. And then for my PIC simulation setup, I want to run this for 20 seconds, and the external field factor, I'm going to use the parameter field factor, and then apply. Then I'm going to paste this value for now, because I mean what we would want to do in the long run is to do a sweep over this range, whatever range we're interested in of accelerating field. So we would have to vary the field factor, but I just want to check for one field factor now, so later I can do a sweep. So that's okay, and I think that everything should be pretty much okay. Okay, one last thing, go to um, special parameters and neglect space charge effects, except it's useful for your purposes, because otherwise it would take extra time. And you could also enable solver setup. You could read about solver stop, so multipacting stop. You could read about this in the help, but this does the automatic stop, but we don't want to do that. I want to calculate up to for the simulation time that I have. So yes, and start the simulation. Now I think this is also going to take time, so I am going to pause the video here and come back when it's done. So that's if everything goes well as planned. Okay, yeah, just checked in the simulation, and you could see, so we should go to particle. We should go to 1-day results, and we look at particle versus time. Then you could already see that there's an exponential increase on the number of particles with time. So maybe I should leave this, is going to take a while longer before it gets to 20 seconds. So I'm looking at this already. I see that at 10 seconds is already sufficient to know if it's going to multipack or not. Maybe in some cases it's 10 seconds is not enough for you to observe this kind of exponential increase. So I'm going to go right ahead and stop this. I'm going to stop this here, and because I don't want to wait for 20 seconds, and since I think 10 seconds is already enough, I'm going to start my sweep. So I'll stop this here, and you could keep the results. So you could keep the results for the simulated time already, and then you could see the emitted secondaries over time, and then you also going to cancel the post-processing. So you see the emitted secondaries increasing over time. So that's the exponential increase. Now for the post-processing, before we do the sweep, because if we were to just run the sweep like this, then this result gets overwritten every time and you have no information about it. So for the post-processing, we'll go to post-processing. I'll just delete. Sorry. I'll just delete this one of results, and I think I'll have to pause it. I don't know what that was. String reaction. So I'll just delete these old results, and for the post processing you go to particles, and then you go to load particle info. And then when you evaluate that, what it does basically is it copies this result to your only result table. Now the webcam is off and it's on again. Hmm. Um, So what it does is it basically copies this, so you have a kind of history of it when you do your sweep. Otherwise, you have no history. So what we um, um, or the way you would record the results would be from looking at the particle versus time, but then you also want to get kind of a pattern. So the number of particles that remain after a particular number of time, which I'm going to make 10 seconds in this case. So for that, we need another post-processing step. So I go to general 1D, and then I go to 0D results from this, and I want the y at a particular x. So I want to get, what I want to get basically is the number of particles that I have at a particular time. So on this plot, which is the particle versus time, I want to get y at a given x. Now I'm going to be using 10 seconds, but the simulation does not exactly get to 10 seconds. So I would make this, I want to get a number of particles at 9.9 seconds. And then, okay, so if I should check for this, I have how many particles. I just evaluated it, and then I'll go to 0 the result, and then I see this. So 6.60 raised to the power 6. Now when you do your sweep, you should have a pattern similar to, where is that here? You should have a pattern similar to this or this, something like this. So I'm going to go ahead. So that's it for the post-processing step. Now I'm going to start the sweep. So the sweep will be over the field factor. So multiplying the field value by the field factor. So let's say I want to sweep from 1 megavolt per meter to, let's say, 40 megavolt per meter. Okay, that's a lot. That's a lot. But yeah, if you were to be carrying out the analysis, then you do that. But let me see. So I'm going from 1 megavolt per meter, 1 divided by 8.3. So this should be about from 0.12 to let's see, then I want to go to 40 megawatt per meter to 4.8. Okay, that's not a lot. Yeah, so 0.1 to 4.8. So I would go to parameter sweep. Okay, so um I'll go to parameter sweep, and I'm not really concerned very much about the warnings, but you should be concerned about it because it's just kind of a demonstration. So yeah, new sequence, and then new parameter, then I want field factor, so from 0.1 to 4 point something, I'll just put 5 to 5. I've forgotten the value calculated. And if I could select the number of samples, but let's see 0.2 steps of 0.2. Oh, step with 0.2. So that is 26. Okay, that's not bad. 26 samples. Okay. No, I don't know how long this will take, but I'll run it and then I'll be back with just showing the results, like results you could get. Now, what I normally do is, if I should run this for a cavity, like a new cavity, then I would run for like big steps. Although 0.1 doesn't seem like a big step, but then I think when you multiply with 8.3 megavolts, then it could be big steps. So that's what I do. I run it for like big steps, and then when I notice multipattern in any region, I refine the step width in that region and run it so I get the profile, like the correct profile of it. So I would only run it for the big steps, and then you should already see you should already see multipattern occurring in the same locations as predicted by this other code, multipack code. So yeah, 26. Okay, I'll just start this, and yeah, that's it. So delete current results, and so yeah, I'll be back when it's done to show the results. So it is evening now. I think I started running the simulation at around maybe 10 or 11 in the morning, and now it's evening. Now I don't think the log file would have information on when I started. Yeah, I think it has information just on the last run, so it's about 6 p.m. So yeah, that took quite a long time, and yeah, that took quite a long time to finish. So, but at least we have results. So this is kind of what you have in the end. So you have your particle versus time for the different field factors. And if I should log this, then you could easily see the one that you, for the field factors that you have an exponential increase, and then you have some other ones that you have a decay after a while. And then you could also see the emitted secondaries. Now my camera went off again. I do not know what is wrong with this. Okay, now it's back on. I think it's my USB. Apologies. So what you get is, what we evaluated was the number of particles at 9.9 seconds. So this is what we have. We could also log it, and then from this you could see that yeah, you have multipacting occurring, which you could also correspond with the particle versus time. This plot, you have a multipacting occurring within this range. So from about field factor of 1.5, which you'd have to multiply with your electric field. So 1.5 multiplied by, let's see, I think it was 8.3 that we had. 1.5 times 8.3 megavolts per meter. So it's from 12.45 megavolts per meter. That's where you, okay, no. The log is quite confusing, because for 12.45 it doesn't quite multiply. So I could say maybe, yeah, from, let's see, maximum from 1.9, so not 1.5. So from 1.9 you start having multipacting, so about 15.7 megavolts per meter. Now what I would normally do is I would refine the step size around this region, and then rerun the analysis for sweep, do another sweep for this, so I have a more refined would I say mesh, accelerating field mesh in this region. So that's what I'll normally do, but then that would take a whole lot of time. And then you could also see from this the field values from which I'm multipacting start. So the green should be at about 1.7. So you already have this. I mean, what I also normally do is I kind of fit an exponential curve with a base to this, and then if the value is above 1, I say it multipacts, and then if it doesn't, because then it shows where there's an increase and also a decrease. But yeah, that's too much information. From this alone, you could already see that, yeah, from about, if I should go with 1.7, then from about 14 megavolts per meter, you have multipacting, and then the maximum multipacting occurs, I mean, using this kind of coarse discretization of the accelerating field at 2.5. So 2.5, and that's at 20.75 megavolts per meter. And this we could compare with the results from this multipack. So for this, it's from 3 to about 6 points, let's say 6.2 or something. So 3 would be divided. So remember that this is peak field. So the axis is peak field. Why? For this we wait. Okay, the axis is for peak field on this plot, while for this one is the field ratio multiplied by the accelerating field. So to convert this to accelerating field, we have to divide by 2. So you see that this occurs, I mean, this predicts a multipacting from between 3 to 6.2. That's about 15 megavolts to 30, 15 megavolts to 32 or 31 megavolts per meter. So 15 megavolts per meter to 31 megavolts per meter. And then, I mean, I wouldn't go into interpreting this curve, but then multipacting is predicted to occur just between like strong, maybe not strong, maybe soft or whatever, but then just between, with this graph, just between maybe 4 points maybe 4 point something to between 4 and 6. Let me just put that for 4 and 6 megavolts per meter. So you kind of have good correspondence um, with the PIC Solver of CST Studio. Now, where did they have their maximum multipacting? It was around 4 point what? Let's say 4.8. Just eyeballing it here. Yeah, 4.8. So 4.8 divided by, so that's 48, because this is times 10 raised to the power 4. So 48 megavolts per meter. So that's divided by 2. That would be around 20. 48, 24 megavolts per meter. So with this quartz discretization, we have our multipaxing at 2.5 times 8.3. So that's around, yeah, 20. So 20, 24. But then maybe if I should maybe refine discretization, maybe it shifts a bit towards 24, which is predicted by the other 2D code. So yeah, that was it for this video. I mean, you could do some other post-processing with the particles versus time. Like I said, you could find the exponential growth factor, or you could also do some statistics with the emitted statistical analysis with the emitted secondary. So but then that's it for this video. One thing I forgot to include was field no, not field monitors, peak monitors. So I have to apparently cancel out of this first. And how do I do that? Yes. So you could include peak monitors where you actually see the motion of where you could monitor the motions of the particle over time. So could put a position monitor and a particle on solid position monitor. So I think maybe that would be another video where I would maybe focus on visualization of the peak. I think, okay, I didn't put any monitor, so I don't have like any I don't have any simulation on that. Now my camera went off again and on again. But yeah, I think that's it for this video before it goes off on me again. Yeah, I think that's pretty much it. If you have maybe questions, you could leave it down in the comment. And I also noticed that 7 minutes of this video would have like bad audio because somehow I think my headphones got disconnected, and then because I had to pause and then like start again. So but yeah, please bear with me because I can't go back to do it because it was before I ran this long simulation. So yeah, that's it, and yeah, till next video. Bye.